Hi, I'm Garrett, and this is Lab Group 3A, Monday morning or Tuesday morning. So we came in and everything was pretty much all set up for us. We had to make sure the laser was aligned, and then we basically this 10x microscope objective, which will work with a 25 micron spatial filter, and then here we have a nice big collimating lens. We're filling the lens aperture. We made sure to align it so that the flat side faces the spatial filter because we're getting a diverging beam here, so that'll give us the least amount of spherical aberration. It is being reflected 90 degrees by this mirror, which has controls for 2 axes of motion. And then we have an iris here that can control how much of the light makes it to our test lens with this 5-pointed Hartmann mask. And we can see in the first steps, once we get our microscope aligned and we allow the light to go through all 5 points, we get a nice diffraction grid. And this is because we have essentially 5 point sources being focused point, and that's what the microscope is focusing on. So we can consider 5 different spherical point sources all interfering in a very symmetric way because the origin is symmetric.
I'm Jeff. I'm normally in group 4B and I was an assembler for this lab. So for this part of the lab we're measuring astigmatism and coma in the system. And to do that we're using a Hartmann mask with 5 holes on it, 1 which is along the optical axis, and then to represent the edges of the field for the vertical for our sagittal plane, and 2 that represent the edges of the field for our horizontal or tangential plane. So what we did is we did at different field angles, which we represented by moving this laterally along the perpendicular to the optical rail 5 millimeters, and we compensated for that by moving this to a field angle by translating optical rail so that we could keep the Hartmann mask filled, and then we adjusted for the field angle by rotating the mirror. So at each of our field angles what we did is we did each hole individually to measure coma, and horizontal ones when we went to our full field point, then when we moved our microscope so that the vertical crosshairs and the spot lined up, that movement that we used for the represented our epsilon. And we know that for coma only our horizontal ones or our tangential ones are going to matter because coma doesn't exist in the sagittal plane. So then for astigmatism we did 2 holes at a time. We did the full field for tangential at the same time, and for this we had to adjust our microscope along the optical rail as well so that we could get our best focus where the 2 beams would overlap, and again translations so that they would coincide with the vertical crosshairs gave us our epsilon.
Data we did for the coma measurements. A and B were the 2 measurements from our right that we did in the horizontal direction, and C and D were in the vertical direction. So as you can see in our vertical direction, our numbers coincided with each other, which is what we expected for a system of pure coma. And with A and B, you can see that our numbers were not the same. They didn't coincide. And we'll go over the picture right here and I'll explain why. So for with pure coma, you can expect that the points, since coma depends on rho squared, you can say that the points at the extremes at rho equals 1 and -1 should coincide. And you can see here at our tangential point, our points don't coincide, and that sort of indicates that we have astigmatism in our lens, or that our system was a little alignment and showed us a little bit of error. But at our sagittal position, our points perfectly coincide, which is what we expect. Orientations of the pinholes. First we measured the vertical and horizontal, and our microscope was at 2 different spots along the rail, 11.37 and 11.27. That gave us about 0.1 millimeters of transverse separation between the sagittal and tangential with our astigmatism. And then we looked at the Y position, the lateral movement of the microscope along the rail, and what that ultimately tells us is what this point is. At a full rho, at rho equals 1, we can find our epsilon value, or our transverse ray value. And if we use this slope, we can find the amount of astigmatism in the system. And essentially, if we had measured the opposite way, we could assume that this line is completed. We can find the astigmatism in our system. And with the other values of H, the other field angles, for 3.5 millimeters and negative 3.5 millimeters, it's a smaller field value. The normalized value is 0.7. So our differences and our aberrations were slightly smaller, but they did show